You're muted anyways, and there's an ad, so I'm just gonna wait until that ad is.
Okay, it's supposed to go to ancient.
History of that. Yeah. What?
Yeah.
Do I need? Aren't those all public? Okay, let me try to. Let me see if I can fix
And
that.
seriously, I'm teaching calculus twice.
Hello and welcome, viewers, to our live stream. Today is another episode of Adrian's History of Math lectures. So we'll be working through. Well, I'll just let Adrian tell you, not steal his thunder.
We didn't organize.
Oh, we didn't organize enough to where he tried to get me to tell him what I was doing today twice, and I still didn't. So as he was saying that, he's like, I don't know what the hell he's doing. Every time he gets up there, I'm scared of what's going to come out of his mouth.
True story.
True story. No, PG. All right, so hey, if it makes you feel better, every time I open my mouth, I'm terrified of what's going to come out as well. So last time we segued, if I remember, I started stealing this from Mark Solomonovich too, because it used to amaze me that he would just show up and then he would muse and be like, what did we do last time? Oh yeah, he was talking to himself, and then he remembers, and then what did we do last time? Last time we were doing conversions of bases and then arithmetic, and I said we would do a multiplication at least once. So let's do one more conversion of the hard conversion. So if you have, first of all, recall, or total recall. We're going to have to get that gif where Arnold is dying on Mars. Total recall. So if we get total recall, what I try to focus on in this series, and then when we're doing this, and then when we eventually post the notes that we're going to have after each of these lectures, etc., we're going to post those for sure after I chop them up. But the bases that we're going to use is base 7 and base 11, mostly because they're the primes on either side of 10. So I want to do this. And last time I did 7s, so let's do a little bit of 11s. But if we're in base 11, the symbols we need are 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we need a unique symbol for 10, so I'll call it alpha. These are my honorary digits, or base 11 digits. Once I do this, we now want to do arithmetic and conversions, etc., from base 10 to base 11 and vice versa. And then if you are just working in this, if you're working in the computer, say, or we use hexadecimal would use A, B, C, D, E, F for the other numbers that we need up to the remainders divided by 16. But the computer isn't going to convert back to base 10 every time. It knows how to internally do the arithmetic and addition and subtraction, multiplication, etc. in all the other bases. So let me do an addition and multiplication, say, possibly in base. And what I'm going to do is cheat and have the base I've already constructed for myself. I'm not going to write it out because it'll take me a long time. I did in my first lectures. It's like I have to write out the addition and multiplication tables base 11. But before we do that, I'm cheating and looking at the notes right now. Let's do a conversion from, did I do one of the easy ones? Yeah, let's do, that one should be easy. Let's do the conversion. Oh, I must have done the conversion the other way, the hard one. Now I can't look at it because I don't know if those are the right numbers. Yeah, I think there's a mistake in here that I still have never yeah. Uh-oh. The number's still, every time I look at that example and grab it, it says convert 312. So let's do this. And then I'll have to use my calculator. Is it the wrong number that I copied and pasted? Base 10 to, I really wanted there to be an alpha there now though. So right now we can edit this part out. You're like, we'll edit this part out. It says convert in the original problem. It says convert 3112 in base 10 to base 11. But then I immediately start with this number. I'm like, those are not the same number. And I think I changed it because I really wanted one of the remainders to be an alpha. So let's find out. So let's conversions. So edit all that crap out. We're going to do conversions from this time base 10 to 11, and then from vice versa, base 11 to 10. This one is the easy one. This one we use the definition of a numeration system. This one we use long division and the division algorithm. All right, so what was the number now? 3107. And now Tim's got his calculator out, or I'll get my calculator out, or well, let's do the long.
I have mine today, man. I
Okay.
have my Mark 1 pencil.
I've got a wet one. It's between my ears. Let's try that. So I have, what am I doing? I have 3107. Let's see which one gives us. I wanted a number that gives me a remainder of 10 when I divide by 11. So because then we have to use the symbol alpha. That was the goal, the pedagogical goal. But then I don't know whether it's this number or the other number. So let's find out. We might change the number in a second. So we're dividing by 11. What you should do, remember, is list the multiples of 11 first. Multiples of 11 are quite nice. Also, that's why I picked the number originally, I'm going to guess. And then Wayne Gretzky's at the end. So now I have the multiples of 11. You can put times 1, times 2, times 3, times 4 is what I try to do. No, not 4 twice, times 6, times 7, times 8, times 9. So now that I have this, what I'm asking myself is how many times is 11? Let's do it all the way correctly, and I'll put it in orange, the one that they normally tell you to stop. But what you do is you say, and then here's the one, 0 times 0. How many times does 3 go into 11? Or sorry, how many times does 11 go into 3? None. None times. And what's the outcome? 0. So we get 3. And they say you can just stop that, and then they tell you a little thing that because that's going to happen, you can just start, and you should just look for the first number that 11 actually divides. But I say do this and follow the rigorous algorithm. It'll always get you there. It doesn't hurt to do an extra step, but if you start skipping steps, you might miss something. Now I bring the next number down. So now I have 31. And now I play the game of how many multiples of 11 are in 31 without going over. And so 31 goes between 22 and 33. So it's going to be a 2. I already have the outcome. I get 22. And then this is also going to show us, I'm doing this in base 10 right now, but we can do this later in base 11. Why do I have to borrow from this guy? This is in the 1 spot. But now the number on the top that I'm trying to subtract, I don't have enough guys in the 1 to subtract 2 from this. So what I do is I borrow a group of 10, and then I get 11 minus this is 9, and then 2 minus 2 is 0. So that's technically how we're doing this in the other bases, so I might as well show you as I do this in the division algorithm for the base 10, coincidentally. So I get a 9, I bring the next one down. Now I ask myself, how many times does 11 go into 90 without going over? It has to be an 8, and I get 88, and I get a 2, and I get 27. This isn't the one, is it? No, because this is going to give me, so it is the other number I must have done. Bah, bah, bah. So what do we get? We get, how many times does 11 go into 27? 2, and we get, oh, I see what I did now. I'm going to backtrack and show you what happened in the notes to show you the errata. I just figured out what the errata was. This is 22, and this gives me 7. And so I thought to myself, well, I don't want the remainder to be a 7 pedagogically. I want it to be a 10 because I want it to be an alpha, so I should add 3 to that number. So then it should be 3110. I could add to the number if I add 3 to that, and we change it. So now let's redo that. I like math. I'm going to do it all over again. So what was it? 3110. That's a good one. Or you could add any multiples of that. So let's now do the long division of 3110 divided by 11. Now let's go faster. This goes into the 0. I subtract. I get a 3. I bring 1 down. 31 gives me 2. I get 22. I'm going to get 9. I bring 1 down. 91 is going to give me an 8. I'm going to get 88. You can steal and borrow if you want. I'm going to get a 3. I'm going to bring it down. No, that still didn't do it. Why did I not do it? Did I do something silly? Did I add the wrong amount to that number? Why didn't it give me alpha again? Duh. It's like when you look back, it's like that I added the wrong amount to the number. We'll get it and eventually. Then that gives me a 2.
I think it was supposed to be 3112.
Let's try this one more time. Math is hard. Yes. Yes, I can't copy from the damn page. So I originally from it says convert 3112 to this, and then I had another number. So 11. 0, 0, minus 3, 31. Now we're going to get it. It's going to show up. Then we're going to get 22. We're going to get 9. 91 is going to give me an 8. 88 should give me the borrow it 3. 32. That is going to give it. Yeah. How many times did I go in there? 2. 22. Math is hard.
It's not math, it's arithmetic.
This is also the philosophy that I like because I was never a smart hoity-toity academic. I'm just a lowly person that wanted to know sciences and stuff like this. So science is not the pursuit of truth. It's just like I just tried to fumble out that sentence. It's completely consistently correcting your errors and your mistakes. So I made a mistake a few times, but this is why I wanted that number. In my notes, I started off with 3107 and then realized that the first one I wanted to get an alpha as this or a 10. So we get 10 here is the moral. So I changed it to this number, and then in my notes I forgot to do this. There's a typo. But now what does that do for us? What that does for us is it tells me that 3112, which is the correct number. Thank you, Tim. Teamwork. Also, though academia tries to say that you don't have integrity if you work with other people, this is bullcrap because everybody works with each other, and this should start being a participation sport. Yes, you have to know how to do the individual calculations on your own, and that's what they're testing for, but nobody does this in a vacuum. You don't just go and sit in a room by yourself. Well, rarely. I do it, but most other people don't want to sit in a dark room by yourself and just read math books. That's going to go, it's much easier to have someone point out that, hey, you should try this or do that. So this fact that, yeah, but all of academia assumes that this is what's happening, right? You just go into a dark room by yourself and do all your homework. Don't get any AI or anybody to help you with this kind of crap.
Isn't that how it works in a sperm donor clinic?
PG.
I was trying not to go there, but I was like, there's many problems that I do, and I play with myself in the dark all the time. But
Fertilization clinic.
but that's the two-player problems. So that's the first rule of two-player problems. If there's not at least 2 players, you're just playing with yourself, and that's called a puzzle. You dirty perverts. That's called a puzzle when you're playing with yourself. It's a game when there's at least 2 participants. Life lessons.
And now back to the history of math.
Now back to this. What was this? I don't even remember now. I've lost track. This was the point. The whole point of that rant was I wanted to, and it took me a little while, but it doesn't matter to me how many mistakes I make, even live on Twitch. I want to get what I wanted to say correct. So the whole point was in base 11, which we're going to convert to, it's not going to be a 10 anymore. We don't have a 10 in base 11 when I actually want to convert this. So whether it's now or later in the algorithm, I haven't really decided. You can give me input into making a correct algorithm for doing this conversion. When you have a base which is larger than base 10, and you have to invent symbols, once you get that symbol, 10 has to be his own symbol. So for right now, because we're in decimal notation, say I could leave it, or we could turn it into an alpha immediately. But 10 is the same thing, equivalent to, or I guess equals, alpha in this base 11. All right, that was the whole point of that. I wanted to get one of the numbers where 10 has his own unique symbol now in base 11, which is called alpha, because it has to be 1 digit. It can't be 2 digits. 10 is 11 in base 11. Okay, now we can keep going. Now let's do the next thing. And what I started doing was, it's Pavlovian. I've trained myself Pavlovian. I put this number in brackets because that tells you in the next step, who should I divide? You use the quotient divided by 11. So the next move is 282. No, not 288. I said 282. 282 divided by 11. So we're going to do the same thing. Every time you're like, how are you getting the quotient to remainder? The division algorithm, which is a theorem, says that any two numbers can always, you can divide one into the other and get a unique quotient to remainder. So let's do it again. Now I have 282 divided by 11. This is going to be what? Technically 0. Now I started it and I was like, now I'm going to start skipping the step, but that's going to be a 0. I get a 0 here, a minus. I get 2. I get 28. 28 is going to be 2. I'm going to get 22. I'm going to get 6. We're subtracting at every step. I bring the next one down. 62. 11 goes into 62 how many times? 5. I check now to make sure that my numbers are right because I have no confidence. That gives me 55. I borrow, I get 12, I get 7. 7 is less than 11, so you can stop in the algorithm. That says that in the division algorithm, that says 282. The dividend is 25, the quotient, times the divisor 11, plus the remainder of 7. Dividend, quotient, divisor, remainder. Again, now 25, and you'll know you get to the last row when you get a number which is less than 11. That'll be the last digit that you get, and then you can block off the last row. So 25, now I don't have to do this in my head, or I don't have to do it in my head, but I will. I don't have to do it on paper. I can do it in my head with what I was trying to say.
The words were there.
So what do I get? 22, I got a 3. That's what I'm doing. So I get 2 groups of 11 plus 3. And then that's where we know we can stop now. The 2 is going to be what? 0 groups of 11 plus 2. So what does that give us? That tells me, and that's last time I claimed that that's the number. Our number now is 3112 in base 10 equals 237 alpha in base 11. And then I just say it, and everyone keeps nods in the lectures, and then they keep going. No one. This is what terrifies me is nobody puts up their hand and says, how do you know that? You just did an algorithm, and I didn't really understand it, and I sat there politely like everybody else, the hundreds that they're jamming into these lecture theaters, and then nobody asks me, well, how? I just said that I'm the king of France. And they're like, oh, all right, I guess that guy's the Dauphin. They didn't even ask like if I'm just making it up or whether I'm lying. Just because I said it doesn't make it true. Things being true make them true. So what do I have to do to convince you that we can do this? Let's do by rote the algorithm. So the first thing I want to do is block off the last row so I don't try to use it in my algorithm. I have a similar one when we get to Euclid and using the Euclidean position algorithm to when we save ourselves from the Germans in 1942 and we'd use the Enigma machine. But for now, we're doing a different algorithm. So what do we have to do? I know that we're going to iterate and change the quotients. I know that 3112 is equal to 282 times 11 to the 1 plus alpha. But now I put that in there. 282 is 25 times 11 plus 7 times 11 plus alpha. And what is that going to be? I distribute that in there. That's going to be 25 times 11 squared plus 7 times 11 to the 1 plus alpha times 11 to the 0. What's the 25? The 25 finally is 2 times 11 plus 3 times 11 squared plus 7 times 11 to the 1 plus alpha. And what is that going to be? That's going to be equal to 2 times 11 cubed plus 3 times 11 squared plus 7 times 11 to the 1 plus alpha times 11 to the 0. And that by definition is 2, 3, 7 alpha in base 11. There it is. That's what you would do in the general theory of the proof, etc. But it's nicer to see in orange, I guess. We're doing, it's not Halloween, but we'll do monster numbers in Halloween and vampire numbers and ghoulish numbers. But there it is. There's the, by rote, in the specific example, the justification for me claiming this statement. Oh. Open sesame. This is the justification. With extraordinary claim requires extraordinary proof. Oh, why are you shutting down? All right, so there's the conversion back and forth. I didn't do back and forth, but The other direction is easier. Why? Because you use the definition. If I want to do, let's do 1 to alpha base 11, 2 base 10, what do? There's a caveat in there because the alpha I have to turn into a 10 eventually, but this by definition is 11 to the 0, 11 to the 1, 11 squared. So this is going to be 1 times 11 squared plus 2 times 11 plus alpha times 11 to the 0, 11 to the 0, which is at some point you have to call this guy 10 because I'm turning it back into decimal notation. So what is that? Now I'm just working with my notation in base 10. This is 121, this is plus 22, and this is plus 10. So we also don't really add that way. So if you're trying to add them, if you're not doing it in your head and you want to line them up, this is the way that you should do it. So I should get 3, 5, 1. So this is 1 to alpha is 153 in base 10. And normally we don't write it because that's the base 10 that we assume that we're using. And you can go round and round if you're checking and you're trying to do these things. Now that you just did that, take this one and reconvert it back into using the other algorithm back into, use the algorithm on this guy and turn it into 1 to alpha. And then round and round we go. So there's the conversion between the two guys. There is a horrible way that Andy Liu showed me to convert from base 7 to base 11 without base 10. But if you don't want to do that and you have to convert from base 7 to base 11, what I just did was use the intermediary. I just turned base 7 into base 10 and then base 10 into a base 11. And then I can convert from base 7 to base 11 if I really want to. So now we have conversions. The other thing we want to do is, I'll just show you, I'm just going to cheat. I'll switch to base 7 just because the table's a little bit smaller and I can look at it. But what I'm doing is looking at the addition and multiplication tables base, well actually here, just wait. Where is this? That's fine. Let me just do it. So this is the multiplication tables. I don't know why I have that in there. So I'm not going to write it out there. Multiplying by 1 doesn't really do anything. So 2, 3, 4, 5, 6. This is why I didn't want to do the base 7. I didn't write out the number 1 because I'm going to assume that everybody knows that, but maybe that's my fault too. 1 times A is A. So I don't need to write it out in the table. It becomes obvious and a waste of space and time. Time and space, space-time. It becomes a waste of space-time. We can do this too if we really want to. No, I'm not going to frickin' South Common to take bikes in. What the fuck is going on? Sorry, I was thinking about something else. At first, this table will look an awful lot like base 10. And because it's base 7, it's going to look weird and it's going to start hopping around. But if you think about this, look at the base 10 multiplication table. It hops around too when we do this because now we're multiplying. Multiplication is higher order addition. M times n in integers really means n plus n plus n m times. So multiplication is addition. But it's higher order addition. This is why BEDMAS is going to work eventually. So what I want to do is Barney's half correct on most of the things. His math is solid. He didn't do very good in any of the other subjects though. But 2 times 2 and 2 plus 2 is 4. No, see, Barney's better than me. I just put 2. That's wrong. Wrong. 2 times 2 is 4. 2 times 3. It is. He does plus though, isn't it? 2 plus 2 is 4. 2 plus 2 is 4. You love me. I love you. We're a happy liar. Liars. Lies from the tablecloth. Love is not a symmetric operation, I'll tell you this right now.
But is it transitive?
No.
Okay.
Absolutely not.
But if
Yeah.
I you and
I can think of counterexamples of me. Hey, there's my Pepsi from last time. Hey, it's like I'll put that there. That'll be for there forever. That's how my brain works. I was trying to avoid your my soul type of question. No, I was trying to come up with a transitivity. My mom doesn't love me, but I love my daughter. Therefore, yeah, if my mom doesn't love me, that should imply that I don't love my daughter, and that would be the transitivity. No, I didn't do it right. Well, maybe that would be true. I don't know. Still, it wouldn't be. If my mom doesn't love me and I don't love my daughter, does that mean that my mom doesn't love my daughter? No, not transitive.
How about reflexive?
Reflexive? Definitely not. I hate myself. You set them up. I knew it. I know what you were doing. I know what you were doing. Can I fill this table in now or what? No, this is the only reason I let you guys come over so we can have some fun with math. Fun math is not an oxymoron. Ooh, we did some English. There it is. So we get 6. 2 times 3 is 6. I'm going to keep going. 2 times 4 is 8. But now guess what we get? Nobody stop me. What's wrong with that?
Hold on, I'm getting your Barney meme.
Okay.
No, you gotta go with, you gotta say 2 plus 2 is 4 again.
2 plus
2 plus 2 is 4. So let's do it. And 2 times 2. We can do the plus tables. But in the plus table, yes, there's the plus. And then we can do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then where is it? The box that is that. Barney, run it. 2 plus 2 is 4. And then it can get dark. And I just imagine just a drunken guy inside that suit that just hates his life. He's like a drunken kid. He's got a strap on. He's all just thick with vodka. His breath is just like, whoa, dude, don't get close to the kids. Ooh. That's got to be a true story. How many Barneys... How many real human Barneys have been in that suit? I bet a bunch because they last like 3 months and they're like, okay.
Barneys have been in the human.
Yeah. PG. Oh, you can Google that. There's a whole website I'll show you later.
I don't know if I want that in the search history.
Off the rails. See, this is why you come here, though, because you won't get this in a regular... You pictured a mathematician talking about the history... Now you're going to take history and math and put them together? I'm not watching that. Yeah, you will, because we're going to talk about Barney being inside you. And that's not going to happen in many...
So I've cut off his microphone for a few minutes until it gets out of his system. Yeah.
I just hurt myself.
All right.
I don't even know what I was doing anymore. Okay, this is 6. Oh, I was trying to bait you, and I baited myself. There is no 8.
There's the obvious line there.
No, don't do it, guys. Don't do it. I'll mute the microphones.
2 times 4 is 8, but 8 in base 7 is 11. Okay? And then what am I going to do? 2 times 5 is 10, but 10 is one group of 7 plus 3, so it's 13, which is really weird. In base 7, multiplying by an even number still gives you an odd number. 2 times 3. What do you mean by even and odd in this different arithmetic? I didn't want to get into there. And then what is this one going to be? I'm hoping it's going to be, if there's any justice in the world, there's a 15, because it should be 2 more than 13. So yes, 2 times 6 is 12, but 12, remember, in base 10 is one group of 7 plus 5 in base 7. And so what we want to do is, now we know that because multiplication is commutative, unlike other operations, this is 6, 11, 13, 15. It goes down the column. You don't have to think about that one also. And then we go into the next one. 3 times 3 is 9, but now 9 is one group of 7 plus 2, so that should be a 12. I'm doing the conversions in my head. 3 times 4, no, oh, that one hurt. 3 times 4 is 12, but 12 is 15 in base 7. 3 times 5 is 15, but 15 is now what? 2 groups of 7. 15 in base 10 is 2 times 7, 14 plus 1. So now what is it going to be? 21. We're going to get. And then the next one should be 3 more than this one, so 24. And then we should get 15, 21, 24. And then what are we going to do? 4 times 4 is 16, but 16 in base 10 is going to be 2 groups of 7 plus 2. So that should be 22, if I'm doing this correctly. And then 26, 33. I'm just going to fill it in now. 26, 33. 5 times 5 is 25. Now try this one more out. 25 in base 10 is going to be what? 34, that's correct. Because it's going to be 3 groups of 7, 21 plus 4 is how you have to do this. And then this one is going to be, I'll just cheat, 42, 42, 51. So at first, but if you look back and you look at your base 10 multiplications, it does this weird pattern too. But if you look at it, everything is symmetric. This matrix is symmetric, which means if I look at what is this, 5 by 5? So if I look at A15, it should be equal to A51, which it is, all the way across, except for the diagonal. It doesn't have to be symmetric. Where's the main diagonal? Main diagonal. Everybody else is symmetric across the main diagonal. So if the matrix in your multiplication is a symmetric matrix, then you have a commutative algebraic operation. Let's do one of these guys, and I'll show you that it truly, and then this also gives a hint in the algorithm that multiplication is just addition, because now if I try to do 626, I don't know why I picked 626, the math class I was in possibly while I first started teaching this, I'm not sure. Because that's the first time I taught this is in Math 160, not in the history of math. But now if we're going to do multiplication, so now you need an algorithm, which is amazing, and what Alan Turing realized when we do this, when he was actually cracking the Enigma machine, and in World War II, women were the computers, because what that meant was they were computing all these trajectories, etc., and top secret things, and they can always get the number correct, even though by definition, because it's top secret, they have no idea what they're talking about. So now I'm going to give you an algorithm, but can you know the algorithm because you've seen it probably at some point in your mind. I give you these two numbers and I say multiply them, and you're like, or do you know it, or has your calculator made you lose this completely? But can you articulate in a finite number of steps on how to do this? It's much harder, and this is what my brain really likes, is taking that vague notion of knowing how to do the algorithm, but you don't even know how your brain is actually doing it. You're just like, I just do it that way, and I just thought it. And the kids are always just saying, well, I just thought it in my head and I know how to do it, and you have to articulate it. So here, I'll give you a precursor. I think I do it in the notes, and I just sucked all the fun out of multiplication. I was like, oh, that sucked the fun right out of that real fast. So I'll just keep that to myself and then give you a slighter version. You're going to get 2 strings of digits in base 7. Take the larger string of digits, put it on the top. Put this small, if I'm assuming there's only 2 numbers we'll multiply, and we'll do 2 at a time because it's called a binary operation, not a trinary. It's not a spectrum. Make sure that the ones digits line up, and then everything will be okay. And then now what we're going to do is, and then why do you add the zeros? What we're going to do is we're going to start with the ones digit, and we're going to multiply consecutively through. If when you do the multiplication of this digit and this digit, if it's a single digit in your table, you can just put the single digit there. If it becomes a 2, and the only ones that we have that are single digits are these 3 in the top corner, anything else is going to be a 2-digit number. So then it's going to contribute this much to the 1 spot, and then you have to carry it to the 7 spot. And this is why you have to memorize addition and multiplication tables, because you're going to see I'm going to rely on it immediately. What is 6 times 3? 6 times 3 is 24. So I put the 4 down and I carry it, because that 4 added to the ones digits in the base 7 representation, but the 2 didn't. It's going to give me the next position. Now I look at this. 2 times 3 is 6, which is good. But then 7, 8, I need the addition tables, but I've done this before. 8 is 11. So this is going to be 1, 1, and I carry it. 6 times 3, again, is 24, and then I get a 25, and then in the last one, you're carrying it over, but you can write it down, 25. And then what do? Why am I adding this 0 now? It's not even rhetorical, Tim. I was like, now that I've moved to, I'm going to move and I'm going to start multiplying in blue so that you can see. Why do I add...
You're in the one group of, what are we in, 7? You're in the one group of 7 now.
Yes, the 2, yeah. When we're multiplying in the 2 by definition is 2 times 7 plus 3. So in the first one we were in the 1 spot and it was adding, but now this digit cannot contribute to the 1 spot anymore, so it's going to contribute 0 to the 1 spot. It's like you've taken the class from me or something. Like
this is why I refrained from answering most of the time.
If you don't know, we're trying to this is also what I wanted to try and do is start doing where we explain it in a way that it becomes comfortable for you to interact with the subject again, because I don't want you to learn these things in the 4 month locally in the class that you're in and then just run away with the rest of your life and be like, there's one time there's one crazy guy showed me how to do that, but then it's been 3 years and I don't fucking know how to do that anymore. Please make these life lessons. Don't binge. You can binge, but you don't purge the math. That's what you don't do. You keep it in there. It leaks out eventually, but I'm never trying to voluntarily purge it. Okay, 2 times 6 is 15. You can cross
That's
those
a
out.
good life lesson, actually. I really like that.
They can cross those out also, yes. Yeah. So 2 times 6 is 15. I carry the 1. Oh yeah, Barney. 2 times 2 is 4, plus 1 is 5. So we can take that win. And then now we're on the home run. In my math classes, if you remember, you're like, I don't remember, I'm trying to delete it. But on the final exam, I always give them a 1 here because 1 times anything is just a number. So then you're like, oh, thank God. Because then you can just copy out 262. But then we're doing...
You're pretty good for your final exams.
Yeah. 2 times... What am I doing? 2 times 6 is 15. Yeah, 15. And then now do you see what we're doing? We're going to have to add. Now we add. And this is backwards. You're supposed to do it. Technically, if you were going to do it, I would rerun the algorithm, but it doesn't really matter because you could just write out zeros in front to make them the same string of digits. I don't want to ruin what was flashed in my head. I'll spare you. But the big number is supposed to be on the top when we add also, but it's okay. It's okay. What do we get? 4, 6, 10. And now I'm looking at the addition table in my mind. 5 plus 5 is what? It is 10, but that's 13 in base 7. 1 group of 7 plus 3. So I carry it. I get 5 plus 2 is 10, so that's 11. And I get 2. 2, 1, 3, 6. Where do we put the comma? Don't use commas, but I guess there you go. In Europe, the comma is the decimal point, so then that can get confusing. All right. There, we did some arithmetic in the other bases. I wanted to get to blah, 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 early spatial warnings. We're going to do that. And then that's where I started making the notes new. I also wanted to get a timeline into, like, can you look up, use Dr. Google, when did we invent fire and the wheel? Just as like data points for, I'm doing a lot of this math and you laugh, but it's like, you'd be surprised at how much math we knew before we invented the freaking wheel. It's like, this math stuff's great, and then we get the wheel later.
So fire was
a long time ago.
2 million years ago.
Yeah, because this is even, these silly people that tried to do, they were going to eat all just raw stuff, not cooked stuff.
Paleo diet?
Yeah, this paleo diet. Well, they had their kids on this, and then the kids just start becoming. Fire's been in our species so long that we need food to be cooked because we've been doing it for so long. We've evolved along with cooking with food, and then there's like, I'm smarter than nature, so I'm gonna force my kids to become frickin' a skinny little skeleton, like that crazy math guy on the frickin' YouTube. That's me. It's like, I'm on the paleo diet. No, you're not as smart as nature. All right, it's blind and it has no intelligence, but it's been going for billions of years. So maybe take some advice from it. Anyways, when was the wheel?
3,500 BC.
Yeah. So
in the West, I guess, in the Mesopotamia and onward, we've had it for as long as we've had written history. But in places like Central America, there's civilizations there, they did so much math before even inventing the wheel.
Yeah,
it's crazy.
Mm-hmm. I always like these facts because that's what I was just scanning through the notes and I started trying to put at the end of the first chapter from the Mists of Time. I started trying to put in the prehistoric dates of like when we actually like formed as a species, and then started getting all these landmark inventions and stuff like that, and the math has to come along with it. Without the notion of a circle, I don't see how they would come up with the fact that you would want to put 6 roots of unity in there, say. Oh, now I blew it. That was supposed to go straight through. And then this is what the Babylonian, so we're going to switch. that was a good segue. Babylon and Mesopotamia. So there's a bunch, there's Arcadians, and there's a whole bunch of these people in there, but for all intents and purposes, I'm going to talk about the Babylonians. And when I talk about the Babylonians, some of the historical guys are going to get into that and say, actually, that was the Acadians that did that, and not the Babylonians, and there was a whole bunch of them, and they were using this. For all intents and purposes, let's just use Mesopotamia to talk about. This means the land between two rivers. So this was the Tigris and the Euphrates in the Fertile Valley, and this is Mesopotamia. I don't remember which one's which, but there's a Tigris and a Euphrates, and this is the Fertile Valley from which our species crawled out of the ooze and started doing math. What they really liked from this, from the symmetry, whether they were trying to make spokes on a wheel for a cart so that the wheels on the bus go round and round, etc., they really liked the number 6, because 6 is perfect. And so that what they would do is divide this sector into 6 points before I start Babylon. And then what they did is they also had a sexagesimal base system. So they had 60. So they would cut each of these. I'm not actually going to do it, but they would cut it into 60. And then if you take those and multiply them, guess what you get? 360 degrees in a circle. Also, 60 divided by 5 is 12, and so you get 12 hours in the clock. And they noticed that there was 2 repetitions of this in a day, so there's 24 hours, roughly speaking, in there. 23 hours, 56 minutes, and 54 seconds, and a few milliseconds in there. And then so every 4 years you have to have a leap year, etc. But this is even from the Babylonians you can thank for having 60 minutes in an hour and 60 seconds in a minute, and then 360 degrees in a circle. And we're going to get rid of this. This is 2 pi radians, you'll see from the Greeks. The Greeks are doing it. And it's not counterclockwise, it's anti-Greek-wise. The clock is anti-Greek-wise. The Greeks did it first. All right, so let's talk about Babylon and Mesopotamia. The Babylonians are using base 60. In most of the history books that I did, they start off with Egypt first, but this is all going on concurrently. And I pick Babylon and Mesopotamia first because the Egyptians realized that the Babylonians had base 60, but 60 is 6 times 10. And so the Egyptians were like, can't we just use the 10 fingers, and then that would be as a much nicer, not 3,600 multiplication table, etc., etc. So the Egyptians didn't quite have a numeration system, but they used powers of 10 in the sub-base system of sexagesimal. So, but the reason I think a lot of the books start with the Egyptians first is because spatial awareness and how we get geometry and those types of things is from the rope stretchers, and Herodotus does this. Herodotus is one of the first historians that notices that they what are you in if you're at the river in Egypt? Denial. Denial. So the Nile would flood every year, and then it would ruin people's land, and then the pharaoh would give landowners money based on the square footage of their land, but then they had to have people that actually knew how to compute square footage. And then you'll see that we get the algebra for why do we call it x squared, and why do we call it completion of squares. We're going to get into that. But if it has side x and it has side x, the area is x times x, which is x squared. So you've never connected probably in your mind, but that algebraic symbol represents a geometric area for them. But then in there on the edge of the Nile, oh, where did it go? We could even make this. The Nile's quite wide, isn't it? Pretty freaking wide. Anyways, you would have your land in here, your plot of land, and then the Nile would wreck some of it in that year, and then it would go away. And so they would have to come out, and then the neighbor would be having disputes, and he would say, no, that piece was mine, and then they'd have to do a bunch of disputes. And so what they would do is they called them rope stretchers, and they can get 90 degrees, and they would go out there and they would calculate all these areas. So a lot of the first algebraic notions and these types of algebraic equations and inventing this. I keep telling my students, as soon as we get algebra, you complain about algebra the whole time, but every time I give you especially a geometry geometry problem or a linear algebra problem, you hate the algebra, you tell me you hate the algebra, but all you use is algebra and you never draw a goddamn picture. Draw a picture, and then it'll become a whole lot easier as to why we call it completion of square, etc., etc. Gods be damned. Coincidentally, I've got a bunch of the quotes, so I'll just read them off and then we can clip them in there later. The Egyptians said, where was this? Let's go to Egypt next. I'll skip down there. In the Egypts, Herodotus said this. So Sistorus made a division of the soil of Egypt among the inhabitants. If the river carried away any portion of a man's lot, the king sent persons to examine and determine the measurement of the exact extent of the loss. From this practice, I think, says Herodotus, that geometry first came to be known in Egypt, whence it passes to Greece. So this was the first one, and then where's the other one? From the Egyptian Book of the Dead, did you bring me a man who cannot number his fingers? So they expected that you could at least count to 10 on your fingers, and it gives a hint into the insight that they were using base 10 because all they were doing was making sure you could count to 10, the digits that you had on your fingers. Okay, let's go back to Babylon. Okay. I just wanted to, I'm going to do whatever I want because Lorenzo said I could. Yeah.
Your lecture, give her.
Let's do that. And so again, this is not historical. I'm more focused on the mathematical ideas and then possibly giving credits to where credit's due to who did this first. So I'm not focusing on historically when the dates happened specifically or these types of things or who did it first. And was it Leibniz or was it Newton? It was like, yes. So I'm more worried about what do we know and how do we know it. I'm far less concerned with whoever did it first. They're all, from my point of view, and that's the classic debate, which we won't go down that rabbit hole either, but we're discovering these things, not inventing any of it. It's already there in the Plutonic universe. We're just carving it out somehow, and our brains are in tune to this. Let's do... Can we go back to... Should we do numbers or let's do some geometry? Let's tie them together.
Dealer's choice, right?
Yeah. So from the Babylonians, they have a bunch of tablets. So let me get those out now too. Old man noise.
They're on Discord. Don't just mention that they're on Discord.
The pictures are on Discord. Okay, yeah. Go ahead. Are you doing it or am I supposed to do it? The pictures
you just
are on.
did great. Yeah, I posted the
I just
link
did.
already. But so the link's in the chat for anyone that wants to view the pictures.
We're still somewhat unorganized, but we're getting a well-oiled machine.
Yeah, it's a machine right now. We're getting the well-oiled part.
Well-oiled part.
Like a 2-cylinder John Deere tractor in 1930.
So this is the Plimpton 322 tablet. What that means is I think it's somewhere, it's Columbus University or something like this. We can look it up. It doesn't really, this is what I'm saying, the historical thing, I don't know. But they went to Babylon and they have thousands of these tablets, and it turned out a lot of them, which is quite amusing to me also, that this is what they called a tablet, and then if you look at the size of a phone thousands of years later, it's awfully similar to the size of the things they were carrying around, but this didn't need to be plugged in. What this is doing is they had rows of, and if you can see it, it's all in cuneiform is the script that they're using, but then they figured out that it was numbers. From the first one, if you look at the first column, it actually ends up just being the numbers. So they're just writing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the other columns, there's 3 columns, and then they were trying to figure out what they are. We'll do this on a different day, but I have a bunch of these tablets and geometry ones. I'll show you a geometry one next. But they had a bunch of recordings, and this is how we know a lot about the Mesopotamians and the Babylonians. So in the first one, these are sides of triangles, I believe, the values of them. And then this one is secant values. So it's trigonometry already that they're doing in this. We'll do this when we get there later. I just wanted to show the tablet. And then another one, this is one of my favorite ones, which is also from there. It's a partial tablet, but then there's a circle inscribed inside a square, and then it's divided out. And what this is in cuneiform. Oh, there it is. There's also, we'll have to take a picture of the back of it. It's on the back. That one, they just glued it on there. So on there. This is from circa 1750 BC, and it is the oldest known recording. It's in the British Museum, and it's the oldest recording of a teacher giving mathematical geometry problems to students. And so this is where the reason I like this one is because the geometric pictures will start deriving algebra for us. Also from this, now I don't know what to do. We're just going to wind down and we'll start Babylon next time. But I wanted to do the connection. So let's do completion of squares. And then I'll figure out where it actually goes. And let's do the sum from I equals 1 to n of I. How did they know how to get, so that what that means is without that horrible symbol, that just means 1 plus 2 plus 3 plus n. And so that's the definition of what that thing is. And then what they want is the closed form. We can talk about Carl Friedrich Gauss. But how are the Babylonians getting to, and the Greeks take off with this and all kinds of things? How do they get the fact that they assume that this would be n plus 1 over 2? If you go to n. And so let's flesh that out. First of all, completion of squares. So they're doing the thing that Herodotus is explaining, or in Babylon they're also doing this. And they have algebra. So what we have is, this is a square, because I said it was. I didn't actually measure it or create it using a compass and a straight edge. But now what I'm going to do is cleverly divide it up like this and make 2 subsquares. So now how many squares are in this diagram? 3. The big one, the little one, and this one. Let's call this length x and this length b over 2. So let's label it all the way. Now what's amazing is you just see this formula. So now let's ignore the picture and let's just do the algebra and what the completion of squares book in the algebra. And I've never seen this one in next to the picture. Rarely when they talk about this in high school or whenever they show you this in grade 8. When am I ever going to need that again? Trust me, you're going to need a lot. When you want to solve ordinary differential equations via partial fraction decomposition and Laplace transforms, guess what? This is going to come up a lot. So they say if you have that guy, first of all, who is that? That's this. It's the area of the blue one. I need more colors. Just a second. Colors. What was Newton doing while the bubonic plague was? Colors. He did Roy G. Biv and gravitation and the calculus of variation in 16 months. Now let's do these 2 triangles. Then it would say plus bx. And so what's this? Well, this one's b over 2x, and this one's b over 2x. But if you add the 2 of those guys up, guess what you get? Bx. And then it says, to complete the square, and then what they're asking was this, and you can see it from now the picture. It seems quite obvious. The thing that I have not shaded was going to be the answer. But when I do that, which didn't I use orange? They're going to say, what's the area of the big square? It's the same formula as this one, but it's going to be what? Equal to x plus b over 2 all squared. And they're like, what do you need to complete the square? This one. And what is the area of that? B squared over 4. So then they would say, well, you need plus b squared over 4. And then you're like, and then the other part that hurts your brain with this, from this picture, from the geometric picture from this, now do you see that that's weird? That this was the area of 2 rectangles, this was the area of a square, and this was the area of a square, and this was the area of the bigger square. So now we've divided the object. This is also how you prove Pythagoras' theorem in many cases, because you just divide up, you draw a geometric picture, and then you get the idea from what the algebra is going to say from the literal picture. And then the other part that you hate from, that I should pedagogically give you also now that we see. So now we can see where the formula comes from. But what do I need? What the first moral of this was, if I have x squared plus bx plus c, and I want to complete the square of this thing, the first rule of completion of squares is get rid of the a. It should be monic. So you do that. So you've divided it out, and you can put the a in there. Good, we've done that. I'll skip that. We'll do this on a whole completion of squares video. But now you're given this, and I want it to look like this. Why are we doing it, first of all? Why the hell do I care? Yeah, I heard it in the background from the peanut gallery. I'm trying to solve from x. But the problem here is, and there's a complete analogy to when we do first order differential equations. If I have dy dx plus p of x times y plus an f of x equals 0, then this is a non-homogeneous first order differential equation. What do I want to do with it? They call this Q usually, I guess. And don't worry about the negative. I don't really care. But what am I trying to solve for here? Y. But there's the exact kind of analogous problem here. In the first one, I have an x term and an x squared term. In this one, when I want to solve, I have a y and a dy dx term, and I want them to be combined into one term, like this. Completion of squares will do that for this. This one, we use the product rule, and we multiply by mu, and then we say, look at this. What would that be? Well, what's the derivative of mu times y? It's going to be leave mu alone, dy dx plus mu prime times leave y alone. Ooh! And then I get separable variable, and then I'm in business. We'll do another video on that, but I got excited from the analogy. Let's step back the analogy. If you didn't know what happened there, I'm connecting. There's a methodology here, and that's what I'm interested in, is the methodology on cracking this. The same problem arises here as in the linear first order difference equations. I'm trying to solve for it, but I got two terms and I want them combined as one. Here, I want these two to be combined. So I want these to be combined. So the first thing they say is you ignore C, you need to look at this guy. So what we need is now, from the picture, we know that we need, what do you have to do? You have to take b over 2. And then I say when it's an actual number, keep both of them, and then square it. And then you're going to get b squared over 4. And then this is what we need, okay? But the other thing that bothers you that they never pointed out is that's what you need in the formula, but I can't just add it to the equation. That's crazy. We're going to add 0. So now I figure out what I need, and I need this to complete the square to write it like this. But I can't just do that, so I subtract it off. And then that gives us another number, and then we can keep solving. This piece now gave me the completed square, and I can write that as x plus b over 2 all squared. Plus, and then what are we going to do? It would start giving us the formula, but this one's missing 4 over 4, so this would be equal to b squared minus 4c over 4. The a is not there because I didn't divide out the a in the regular formula, but you can already see that Francois Viette is there. After I show how to complete the square, someone will always put up their hand and be like, can I just use the quadratic formula? Yeah, how do you think they got the quadratic formula? They completed the square on the general form. It's the same damn thing, no connection. This always scares me, these types of questions, because there's no connection whatsoever to the thing that you've memorized to actually knowing what the fuck is going on. So it is the same thing, but there's two parts that you hate in completion of squares, which this just turned into. Please, can we do completion of squares? It's a geometric picture. The completion of squares is the little square, but you can't just add that in. You have to add it in as 0. And then you get the completion of squares that you want. And then, as the disembodied voice behind the curtain said, you can solve for x now. Once it's like this, I can solve for x and do square root and plus minus, etc., etc. All right, let's do one more rant and draw one more pretty picture for this guy. Oh, also, in this one, sum from I equals 1 to n of I is n plus 1 over 2. Carl Friedrich Gauss does this at age 5. Should I show that one? Maybe we'll show that one in a second. But this is the closed form. This is the definition of what it is, and this is the closed form. Because that's exactly how this is. So these two different forms are what I guess we're going to tell the story first. Carl Friedrich Gauss is 5, and his German or Prussian instructor doesn't want to deal with all these kindergartens, the garden of kids. And so what he says is he's like, take the first 100 numbers, 1 to 100, and there's memes on the internet of this. If you got $1 and they gave you one more dollar on each step, and you climb 100 steps, how much money do you get? $5,050. How did I come to this conclusion as fast as Carl Friedrich Gauss did? Here's how he did it. So what the instructor thought was going to happen was the kids are going to do this. They're just going to do 1 plus 2 is 3, and then you add a 3 is 6, and then you're going to go all the way, and you're going to have to add those numbers linearly all the way out. And Gauss is like, that's crazy. He's like, I want a closed form of it, so I don't have to add it that way. I could just say, what is the number 100? 100 divided by 2 is 50, times 101 is 50/50. So how does he do this? What Carl Friedrich Gauss says is he says, well, let's call it S, the power of algebra. So that's this guy. And he says, well, I'm going to call it S, but he's so clever, I'm just going to write it backwards. How many guys are in this? N, so let's add them. So I get 2S is what? N plus 1 plus ... plus N plus 1. But how many of them are there? N. So by definition, that is N times N plus 1 of multiplication. So S is equal to N plus 1 over 2. But he already has algebra in the 1700s. So Gauss did he was 5. What were you doing when you were 5? Not this, I'm going to suspect. But the last thing that I'm going to show is how did the ancients do this? And you can do this with a whole bunch of them, and you can get much more sophisticated. So that's how Gauss did it, but he had the power of algebra. How do I do this without algebra? Pretty pictures. Let's do N is 3. And this is on the Mario Ghost chip, the triangle coins, or this is a triangle number. So this is N equals 3. And what they're going to do is, they're going to do this. They're going to fill out so now there's 2 triangle numbers, but now I've got a number. But now that's 3 times, let's call it 3 plus 1, which is 4. Barney, you're correct, but that's not the only way I can get 2 plus 2 is 4. There they are. There's both of the ways with the integers less than 4 to get 4. I couldn't help myself. And then what is our number, though? The actual number. So what they want to know is how many numbers are in this orange triangle. Well, it's half of this rectangular array. How many dots are in the rectangular array? 4 times 3 divided by 2. In the general array, what would there be? There would be n plus 1 over 2. And what is that? If you look at that, that's 1, 2, 3, 4, 5, 6. That's the sum from I equals 1 of the first, here's 1, and then 2, and then 3. So what is that? That's 1 plus 2 plus 3. No, this one is 1 plus 2 plus 3, which we would call in modern language sum from I equals 1 to 3 of I. So, and what was that? That was 3 plus 1 over 2. So they're using what they call triangle numbers and dots in arrays, and we'll get into that when we do the Greeks. But this is how they come to the conclusion from a geometric picture to an algebraic formula of how they were doing all of this. All right. I'm out of coffee, so I think that's where we end.
All right. Thank you, everyone. We'll see you next time for another episode of History of Math. Goodbye, everybody.